So this is the third video on the group 2 elements. So if we keep track of where we got to, in the first section we looked at the trends in the group 2 metals. Then the second section we looked at how they react and how you make different compounds of them. Now we come to a section where we look at the behaviour and trends of those compounds rather than the metals themselves. The first thing we look at is the uses of some group 2 compounds. So we know we can make them by adding these metals to water or reacting with oxygen, but how do we actually use the compounds we make? The first common use we look at is for magnesium oxide. Magnesium oxide is used in indigestion remedies to react with excess stomach acid. We looked in the last video the fact that group 2 oxides actually act like bases, so will react with acid. So hydrochloric acid is in stomach acid, making a salt plus water, which will neutralise it. Magnesium oxides found in antacids. You might have heard of milk of magnesia, would be an example of one, which contains this to neutralise any excess stomach acid causing indigestion or heartburn. Similarly, calcium carbonate again will react with acids. Carbonate plus acid goes to salt plus carbon dioxide plus water, which will neutralise it. So you find that in toothpaste, and that will neutralise plaque acid. Again, you wouldn't really need an equation here because you don't know what plaque acid actually is. We have a little bit more detail on the calcium compounds to look at, and there's kind of two main reactions which sum up their uses. If we take calcium carbonate, that's a material known as limestone, and a very useful reaction of limestone is that we can thermally decompose it, which means break it down using heat. If you decompose limestone, calcium carbonate, you get calcium oxide plus CO2. We'll come back to calcium oxide, but if you react it further by putting it in water, again that's a reaction we've looked at in the previous section, you'll convert it into calcium hydroxide. So we'll need an extra, no, in fact that's wrong, sorry, just one H2. So let's look at the uses of these reactions here. First one's calcium oxide. So if this is limestone, calcium oxide is known as quicklime in a historical sense. Where you'll find quicklime being used, if I bring in the wee picture here, this is a lime kiln in County Mayo. So all over Ireland you will find the remains of these kind of stone structures with little holes in the middle, which are known as lime kilns. One historical thing about Ireland is obviously it's very agricultural. The problem is our soil is actually quite acidic, so it's quite hard to grow lots of crops there. What ancient farmers worked out was that if you sprinkle quicklime, calcium oxide, onto soil, it will make your crops grow better. And they probably didn't realise why that was, probably just knew it was a magical white powder that makes their crops grow better. But if you think about it, you're making calcium oxide by heating limestone and thermally decomposing it. The calcium oxide is a base, so if you put it onto an acidic soil, it will neutralise the soil and give you a much better pH for growing crops. So that was one ancient use of calcium oxide. Another ancient use was in an early form of cement or concrete. This is the Pantheon in Rome, which is like an ancient temple built about 100 AD. Again, it's amazing to look at how much detail and structure they will do back in those days. A lot of it came from the Romans' discovery of what they call Roman concrete, which was a mixture of calcium oxide, quicklime, mixed with volcanic ash to bind it together. And with this ancient form of concrete, they were able to make these amazing structures. Another use of one of these calcium compounds is this calcium hydroxide. Calcium hydroxide in solution is known as lime water, which obviously you know is a very common way of testing for carbon dioxide. What historians reckon lime water was used for back in the day was as a hair treatment. They have this account from this Greek historian who had this thing about the Celtic people he discovered. They're terrifying in aspect, they're tall in stature, their hair is blonde but not naturally so. They bleach it to this day artificially, washing it in lime and combing it back from their foreheads. So this lime he refers to is probably lime water. Calcium hydroxide dissolved in water. And what the Celtic people discovered is if you wash your hair in it, it bleaches it white and makes it kind of dry out and stick up on the end, which maybe make you look a wee bit more terrifying. They reckon the statue's trying to show what that looked like. So if you're ever stuck in the pinch girls during this lockdown, just get some lime water and use that to bleach your hair. So in terms of what you need to know, covered most of this paragraph. Calcium carbonate is limestone. It thermally decomposes to calcium oxide, otherwise known as quicklime. If you react that quicklime with water, you get calcium hydroxide, which is known as slaked lime. And if you dissolve that slaked lime in water, you make what's called lime water. The terms aren't particularly important, that just gives you a bit of context there. The one specific use you are meant to know about is modern cement. I know we mentioned Roman concrete, but cement to this day still uses calcium oxide. What you do is you mix it with silica. Silica is like a material you dig up from the ground, which is a mixture of two compounds. It's a mixture of sand, which is silicon dioxide, and aluminium oxide. So those two things together make silica. When you add water with calcium oxide and silica, you get two side-by-side reactions taking place. The calcium oxide can react with both the sand and the aluminium oxide. So these two reactions here show that. Calcium oxide reacts with sand, so that's silicon dioxide, to make something called calcium silicate. That might ring a bell. That's actually one of the 5 reactions of the blast furnace. You might remember from last year. Calcium silicate is otherwise known as slag when it's molten. But in this case, this is useful in cement. Calcium oxide also reacts with aluminium oxide to make this very complicated looking compound called calcium aluminate. That's the aluminate ion right there. I wouldn't worry too much about these equations. I mean, they are given to you there. If you can learn them, probably do. They've never come up in an exam though, but I guess they could if they're being particularly mean. But this mixture of calcium silicate and calcium aluminate are known together as cement. So when you add water to it, those two things can react together and bind and give you a cement to stick things together with. So there's some everyday uses or modern uses of group 2 compounds that you might want to make them. The next little bit on the behaviour of these group 2 compounds, so it's not so much about the use now, it's about how they behave physically. A bit on the thermal stability of the group 2 compounds, specifically the carbonates and the hydroxides. There's a couple of trends you're meant to know here. So the thermal stability, what we mean by that is how resistant it is to being broken down by heat or thermal decomposition. So if you've got something which is very thermally stable, it'll take a lot to get to break down with heat. If it's not thermally stable, it'll break down quite easily using heat. If we're talking about the group 2 carbonates and hydroxides, we've got 2 different decomposition reactions going on. So this is a metal carbonate. If you heat it, it'll break down into a metal oxide with CO2 given off. If you've got a metal hydroxide, a group 2 metal hydroxide will break down into a metal oxide plus H2O. So we're trying to get an idea of how that will change down the group, how easy that reaction is to do in both cases. So we've got a little trend to explain. I'll talk to the paragraph in a second, but it helps, I think, if I draw a picture first. So I want to do a wee comparison because we have to know the trend going from top to bottom of group 2. So if I take just 2 kind of extreme examples, magnesium is quite near the top of group 2. So if we look at magnesium hydroxide, I could look at magnesium carbonate. Hydroxides may be a bit easier to draw and show. And I can compare it to one from the bottom of the group, barium hydroxide. So magnesium close to the top, barium close to the bottom. We're looking for any differences in how they might decompose with heat. So if we think about the differences between magnesium and barium, obviously they're an ionic compound, so they have the same charge. So what this compound looks like, drawn out a wee bit more structurally, it's a magnesium 2 plus ion with ionic attractions to 2 hydroxide ions. So that's OH minus, the minus charge is actually on the oxygen. And same here. Magnesium is actually quite a small ion in the grand scheme of things. We'll come back to that, why that's important. Barium hydroxide is still got a 2 plus charge, but it's right down the bottom of the group. We talked about the trend in atomic radiuses. It's a really, really large ion, which has an attraction to 2 hydroxides. So we're going to bring in a new term here called the charge density. If we compare magnesium and barium together, they both have the same charge. They're both 2 plus because they're in group 2. However, that charge is not spread out over the same area or the same volume. Barium is massive compared to magnesium. Therefore, that 2 plus charge is quite spread out and dispersed. Magnesium is quite concentrated. The term we'd use to describe how that charge is spread out is called the charge density. We would say that magnesium 2 plus has a much higher charge density than the barium 2 plus ion. If you got really high charge density, it means your charge has a much more strong effect on things it's bonded to, because it's a lot more compact, a lot more compressed, the charge into one little space. That means that this magnesium 2 plus ion will have a much larger attraction, much more intense attraction to the ions attached to it. Now, this is where it gets a little bit confusing. If we're saying that magnesium has a much stronger attraction to the hydroxide ions than barium does because it's much more charge dense, that would probably lead you to believe that magnesium hydroxide should be much more resistant to breaking down with heat compared to barium hydroxide. That would be a very reasonable thing to kind of assume. We actually get the opposite trend being true. Magnesium hydroxide will break down much more easily with heat compared to barium hydroxide. The reason for that is this. The effect of having a really high charge density in a compound within an ion, a metal ion compared to the ions attached to it, is that charge density can actually destabilize that ion. In other words, it can be attracting that ion to such a large extent, it actually destabilizes it. The effect is, it's what we call polarizing the ion. So if I draw that OH bond in there, the attraction between this oxygen and that magnesium is so intense, it actually weakens the attraction between the oxygen and the hydrogen there. All the electron density is pulled straight towards magnesium. That actually weakens this bond, or these two bonds between the O and the H, which actually means that they can break down much more easily due to heat and break down into magnesium oxide. So we've lost that H and an H2O where this OH minus comes off as well. In contrast to the barium, whilst the attraction between the barium and the hydroxide maybe isn't quite as intense, it actually helps it because it's not as destabilized, this hydroxide, and because the attraction isn't as big. So it's actually quite happy to sit there. It's still got reasonably strong attraction with the 2 plus charge, but not so strong it's actually going to polarize or destabilize that hydroxide ion. So barium hydroxide will actually be quite stable at high temperatures. So it's all to do with charge density, causing a destabilizing effect on the ion attached to the metal, which means actually it's quite easy to break it down with heat. So showing how that's written down in a paragraph, I will read through this. The thermal stability of both the group 2 carbonates and hydroxides increases down the group, so it's more stable with things down the bottom like barium. I showed you that for hydroxides, but that will still be the same case for carbonates as well. Down the group, the size of the cations increases, while the charge in the cation is maintained at 2+, so they're all 2+ because they're in group 2. This means that the charge density decreases down the group. So whilst the attraction between the cation and the anion decreases down the group due to the reduced charge density, so that might make you think that it's going to be destabilised, it actually does become more stabilised. Cations at the top of the group, like magnesium, have a high charge density, and this causes a destabilising, polarising effect on the ion, so causing it to break apart into kind of two halves because it's so attracted to the cation, causing it to be less thermally stable. So that's a wee bit waffly. In terms of the exam, if you wanted like a nice 3-point definition to learn off about how you explain why it's more thermally stable down the group, you'd say this: the size of the metal cation increases down the group. This causes the charge density of the cation to decrease down the group. Therefore, if it's lower charge density on the group, the cation is less able to polarize and destabilize the carbonate or hydroxide ion, whichever one you're talking about within the question.